Welcome everyone. Vanadium is a transition metal. In this video, I'll illustrate examples of cis-trans isomerism in complex ions. Next, I'll show you how to derive a balanced equation for the production of vanadium 5 oxide. In the final part of the video, I'll describe the chemical equations that show how V2O5 acts as a catalyst in the manufacture of sulfur trioxide. The questions are taken from an A-level chemistry exam paper. Details are in the description. Let's get started. Here's the first part of the question. The VH2O4Cl2 plus ion exists as two isomers. One isomer is shown. Draw the structure of the other isomer and state the type of isomerism. Transition metals, including vanadium, often form complexes with an octahedral shape. The central metal cation, vanadium in this case, makes 6 coordinate bonds with ligands. The ligands present in this complex are chloride ions and water molecules. The complex ion is shown in square brackets with the overall charge on the ion at the top right. Octahedral complexes might exhibit stereoisomerism. Stereoisomerism includes optical isomerism and cis-trans isomerism. Water molecules and chloride ions are both monodentate ligands. Each of these ligands forms one coordinate bond with the central metal cation. The type of isomerism shown is not optical. At least 2 bidentate ligands must be present for an octahedral complex to show optical isomerism. The structure of the other isomer is shown on the right here in blue. To help you get an idea of the three-dimensional shape of these isomers, the photographs at the top show the structures built using molecular model kits. Chloride ligands are green, water ligands are red and white. The type of isomerism is cis-trans isomerism. The isomer on the left is the cis isomer and the isomer on the right is the trans isomer. Here's the next part of the question. Heating NH4VO3 produces vanadium 5 oxide, water and one other product. Give the equation for the reaction. We can start by putting the formula of the reactant NH4VO3 on the left and one of the products, water, H2O, on the right. We can use oxidation states to work out the formula of vanadium 5 oxide. The oxidation state of vanadium in this case is +5. The oxidation state of oxygen is -2, and the sum of the oxidation states is 0. Vanadium 5 oxide must have the formula V2O5, and this is now shown as a product on the right. We have to think about what the other product must be. Heating ammonium compounds could produce ammonia. The equation needs to be balanced for nitrogen, and ammonia is a common compound that contains nitrogen. Finally, we need to balance the equation. The question is now complete with the full balanced equation given in blue. Here's the final part of the question. Vanadium 5 oxide is the catalyst used in the manufacture of sulfur trioxide. Give 2 equations to show how the catalyst is used and regenerated. Transition metals and transition metal compounds are often used as catalysts. Transition metals have variable oxidation states. Intermediate products can be formed in which the transition metal has a different oxidation state. Catalysts provide an alternative reaction route with a lower activation energy. This alternative route could be via a transition metal intermediate. The equations that you need to answer this question are on the AQA specification. You have to know them. It's what I refer to as memorizable content. The answer to the question is given in blue. If you haven't memorized these equations, it might be possible to construct them. In order to do this, you'll need to know the overall equation. Adding the 2 steps together and cancelling down will give the overall equation. In this reaction, sulfur dioxide is used to make sulfur trioxide. Oxygen, in the form of O2, is readily available in the atmosphere, so a sensible overall equation is given there at the bottom. The catalyst, V2O5, must be used up in the first step and regenerated in the second step. If V2O5 reacted immediately with oxygen, it wouldn't be a particularly stable catalyst, so it makes sense that SO2 reacts with V2O5 in the first step. This means that oxygen must be a reactant in the second step. There is no sulfur in the second step, so it is most likely that the SO3 product is formed in the first step. Finally, balance for atoms. We can see that the V2O4 intermediate is produced in the first step and used up in the second step. Once again, we've arrived at the same two steps given in blue. It's much easier to memorize this content. However, the skills required to construct two-step equations like this are also linked to developing inorganic reaction mechanisms from the rate equation. Thanks for watching. Please post in the comments if you have any questions or suggestions. Take care and good luck with your studies.